Hello students, in the last lecture I told you about basic of crystal structure and the lattice. Before going to the detail of the crystal structure, in this lecture I will be talking about symmetries. So in a crystal there are different kind of symmetries are found. So these symmetries are a set of mathematical rules that describe the shape of an object. In a crystal, a symmetry is simplifying to unfold the crystal structure in some known pattern. So, if there is symmetry, then it can define the whole structure of a crystal. It is a definite ordered arrangement of the faces and the edges of a crystal. So the crystals possesses different symmetries and are described by certain operations called symmetry operations. These symmetry operations leave the crystal invariant when it is applied on it. If these symmetry operations are being applied in successive manner, then ultimately it should bring the body into the original state. The symmetry operations are of two types. The one is which is performed about a point or a line, which is called point group symmetry operation. The symmetry operations which are performed by translation along with the rotation is called space group symmetry operations. So the point group symmetry operations are of three types. First is inversion or center of symmetry, second is reflection symmetry, and third is rotation symmetry. So in the inversion symmetry, a crystal possesses inversion symmetry if there is a point in the lattice and the lattice point is situated at position vector r with respect to that point, and there is a corresponding lattice point at the position minus r. So if there is such point in a body where the lattice points are situated at r and minus r position, then a crystal is said to have a inversion center or center of symmetry. The cubical structure has the center of symmetry at the body center. Now, if you see here, this is the center and this point and this point are at same distance from this center point. So this center point is the center of symmetry. So this center of symmetry also works for this corner and this corner, similarly for this corner and this corner. So in total it possesses three pair of parallel and opposite faces equidistant to the body center. Thus, the inversion symmetry in a crystal is equivalent to the reflection through a point. As you can see, the reflection of this point is this point, and the reflection of this point is this point. And this is the point of reflection. Coming to the second symmetry, which is reflection symmetry. So a crystal possesses reflection symmetry about a plane if the crystal remains invariant after being reflected by the plane. So here you can see in the cubic crystal there is a center plane and it is the plane of symmetry because the reflection of the lower plane is the upper plane. Here also there is one plane which shows the plane of symmetry, similarly here. Also at the body diagonal there are 6 plane of symmetry in the cubic crystal structure. So in a cubic crystal structure there are 3 plane of symmetry parallel to the cube face and 6 plane of symmetry along the diagonal planes of cube. The third is rotation symmetry. So a crystal will possess rotation symmetry about an axis if the crystal remains invariant after being rotated by some angle about the same axis. That angle, let's say if it is phi n and is given by 360 by n, so 360 degree is the complete rotation, then the value of n will define the fold of axis. Here if you see, for the cubic crystal, there are three kind of axes are there. One is diad axis, one is triad axis, and one is tetrad axis. One important thing with the rotation symmetry is that it can have 1, 2, 3, 4 and 6-fold rotation symmetry, but 5-fold symmetry is missing. The tetrad has 4-fold symmetry, the triad has 3-fold symmetry, and the diad has 2-fold symmetry. That is why the name reflects the fold of the symmetry. Now, as we learned that 5-fold rotation axis is not compatible with the lattice, so let's see why it happens. So consider a lattice row x, p, q, y. So there are 4 lattice points at x, p, q and y, and because these are lattice points, so they will be separated by same distance. So let's say the distance that is a. Now if we rotate the xp in the clockwise direction and qy in the anti-clockwise direction, and the new position of x is p1 and the new position of y is q1, then the distance between p1 and q1 should be the integral multiple of the lattice constant a, because if it is showing a rotation symmetry, then this new position should be the position of some lattice point. So now we can assume that P1 Q1 is equal to MA, where M is some integer number. So from figure we can see that cos phi n is equal to P1R upon PP1. So we can get the value of P1R is equal to A cos phi. Similarly, SQ1 will also be A cos phi. So the total distance P1 and Q1 will be P1R plus RS plus SQ1. Now here RS is equal to A, because if you draw a perpendicular line at XPQ and PQY, then it will cut at R and S. So as PQ is equal to A, so RS will be A. So the total length of P1 Q1 will be A 1 plus 2 cos phi. As we know that P1 Q1 is equal to MA, so from the previous equation we can equate these two, and then we will get the value of cos phi equal to m minus 1 by 2. So in place of m minus 1 we can put n, which is also an integer. Now as n is an integer and cos phi can have value between minus 1 and plus 1. So if we use n from minus 2 to plus 2, then n by 2 will be from minus 1 to plus 1. And because cos phi is equal to n by 2, so cos phi will have the same value. So from here if we put the value of cos phi, then we will get the value of phi, and then from there if we calculate the value of small n, 360 by phi n, then we can see there is 2, 3, 4, 6, 1, but there is no 5. So it means the 5-fold crystal symmetry does not exist. There is another symmetry which is called rotation inversion symmetry. In the rotation inversion symmetry, the rotation and inversion both are performed together, and they are performed until the original position is obtained of the body. So here for example, let's say there is a point that is point 1 and it is rotated to the 4 and then get inversion and reach to point 2. Now, if we want the point 2 to reach to the original position 1, we have to perform this operation again. So again if we perform this, then 2 will rotate to 1 and 1 will get inversion to 3. So again if we will rotate from 3 to 2 and then from 2 it will get inverse to 4 and then from 4 if we rotate again to 3 and then after inversion it will reach to 1. So finally after 4 operations the point 1 will come back to its original position. So it means this symmetry is 4-4 symmetry. However, a crystal can possess 1, 2, 3, 4 and 6-fold rotation inversion symmetry. The next is translation symmetry. So if in a space lattice there is a point which is translated by this relation where a and b are lattice vector and n1 and n2 are a pair of integers, then if in this translation, if the crystal structure remains invariant, then the crystal is said to possess translation symmetry. Typically, these translation symmetries are very small and that is why they are macroscopically not visible. So this is all about the symmetry. In the next lecture, we will talk in more detail about the crystal structures.